Hello, and welcome to Burris Agronomy U. This is Matt Montgomery, sales agronomist with Burris. We're entering into part 3B of what's turned out to be a 9-part series rather than the originally intended 8-part series, and the topic is sulfur. You may remember the reason we stretched this out. The topic area, plant available sources of sulfur, was just too big, and we needed to really break that section apart. So last time we talked about organic sources of plant available sulfur, and this time we're going to talk about atmospheric and fertilizer sources of plant available sulfur. As always, though, we want to review where we've been quickly, and we want to talk about where we are in the outline for this series. So this is where we are. We are in the second half of our third section, this topic of major plant available sources of sulfur. We began this series by talking about basic information, talking about what the plant uses sulfur for within it. We talked about the series theme, and we'll reference that here in just a second. And we talked about how sulfur actually gets into the soil sulfur cycle through atmospheric deposition and the application of fertilizer. From there, we talked about plant availability. We talked about sulfate, that negatively charged form of sulfur, being the way that most plants actually draw in their sulfur, being the major source of plant availability. We talked about sulfate not being held tightly by the soil and floating within soil water, being drawn in with the water stream. And from there, in section 3, we talked about organic material. And we mentioned that organic material, that source of sulfate, is perhaps one of the most important sources of sulfur annually. The theme for this series, and we keep driving this point home, is always, always, always look to the soil sulfur cycle. We study the soil sulfur cycle because it helps us answer many of the questions growers have that you may have about the sulfur cycle itself, about this topic of sulfur and sulfur fertilization. We referenced this, and I'm going to reference it again. When you look at the major sources of plant available sulfur, I really break down those sources in this priority. Organic forms of sulfur represent the primary source of plant available sulfur to the plant. That's followed by atmospheric deposition, and that is followed by fertilizer. So let's talk about atmospheric deposition right now. Atmospheric deposition is sulfur basically actually falling out of the atmosphere into the soil. We're going to talk about that process just a little bit. But again, the goal is to get to sulfate. That's the form of sulfur that's primarily taken up by the plant. And you can see there's a very direct, clear pathway from the atmosphere, sulfur being deposited from the atmosphere into the soil so the plant can then take it up as sulfate. Now, my goal is not to make everybody a chemist when they're watching this thing. And so if chemical formulas overwhelm you, I want you just to avert your eyes and turn from the screen, and you can turn back a little bit later on. Just listen to what I'm talking about, and that'll be good enough. If you do, though, want to know what the chemistry looks like behind atmospheric deposition, that's right on the screen in front of you. I want everybody else, though, to hear these words, acid rain. Sulfur is deposited from the atmosphere with rainfall in the form of what we call acid rain, and it actually is fairly variable how much sulfur you get through acid rain. It can be anywhere from 5 pounds per acre per season to 40 pounds per acre per season. And the reason there's so much variability has a lot to do with one's proximity to coal-burning power plants. Now, worldwide, a lot of the sulfur that's deposited by this slight acid rain that occurs in most of the world is really from volcanic activity or gases being released from the ocean. But around here, around the Midwest, this thing that actually has some negative environmental consequences also has this positive with it in that acid rain actually deposits a lot of sulfate into the soil profile. So that's our quick nuts and bolts discussion of atmospheric deposition. Really gets you to the place where you understand that topic the way I think you probably need to if you're going to talk about sulfur with anybody. But I want now to talk about fertilizer. And just like we did last time, instead of us just talking through the cycle, I'd like to kind of talk about a real practical, real world problem or question. And I want it to be this one right here. Why is elemental sulfur not a good quick fix for a sulfur deficiency? Why is it more of a long-term fix? And why does it acidify? And you already know what I'm going to do. I'm going to say to answer that question, we need to look to the cycle. Instead of us talking about elemental sulfur, though, to answer this question, let's begin by talking about sulfate fertilizers. So elemental sulfur is on the lower right-hand side of the screen there. We're going to talk about sulfate fertilizers to begin with. And I want to remind you what the goal is. We want to quickly get to plant uptake. If we saw a yellowing in the field and we wanted to correct that yellowing quickly, we would want to get to plant uptake as quickly as possible. Now, when we apply sulfate fertilizer to the soil, it eventually breaks apart. And as it breaks apart, one of the things it immediately breaks apart into is sulfate. And that already should sound like good news to you from the sessions we've attended before. And the reason we say that's good news is because we know that sulfate tends to be the form of sulfur that is taken up by the plant. The plant will now draw water into it, and because sulfate is floating in the soil water, it will be taken in with those water streams, and that means something. It means that sulfate fertilizers quickly reach the goal. They go from fertilizer application to very quickly plant uptake. It's a very efficient process. Now, if you just take a moment to look at the position of elemental sulfur on this diagram, you begin to get this feeling that it's not nearly in as good a position as sulfate fertilizer is if we want to get it into the plant immediately. Just look at how far removed it is from that diagram portion that says sulfate. And look at how far removed it is from the goal. The goal is plant uptake. Look at how much elemental sulfur sits on one side of the graph while plant uptake sits on the other. So there really is quite a process that we have to engage in to get elemental sulfur into a form the plant can use. It starts out as elemental sulfur, but then it has to be transformed. So just like with organic sources of sulfur, we have to have bacterial oxidation. And we talked about what that was last time. If you don't remember some of these terms, it might be worth going back and watching the previous session. And only then, after bacteria have oxidized that sulfur, after they've formed sulfate, do we have that opportunity for plant uptake. And you can see right here, elemental sulfur really takes a while to get to that goal. It's not nearly as efficient as sulfate fertilizer is at getting to rapid plant uptake. And that's one of the reasons why elemental sulfur really works better as a long-term fix for sulfur deficiencies rather than a quick-term fix. This means elemental sulfur can be a nice long-term fix, but it also means that elemental sulfur is not a good fix for sulfur deficiency, not a good immediate quick fix. There's too much of a delay between application and transformation into sulfate. It's just not going to allow us to see that rapid remedy of the situation. Remember, we also did not just ask if elemental sulfur was a good or not so good source for solving rapidly sulfur deficiency symptoms. We also asked if it was something that could acidify and why. And it can. Elemental sulfur does acidify, and this is the reason why. It goes through that same bacterial process of conversion of sulfur into sulfate that we saw with organic sources of sulfur. And in that process, you'll remember from last time, hydrogen cations are released, which creates that acidity that we're talking about earlier. That's the source of that acidity that we mentioned previously. It's also important for us to talk about one other thing, and that is there's always this mechanical component to fertilizer applications. Fineness of grind always comes into play. Large particles just are not going to solve problems in the soil as rapidly as small particles. Small particles will break down, bacteria can reach them, they have a greater surface area, those kind of things. Whereas large particles take a much longer time to degrade. So fineness of grind comes into play here as well. And if we have really small fineness of grind, we're going to see more rapid conversion to sulfate and better plant uptake. We spent a lot of time talking about elemental sulfur, and actually in the industry oftentimes we will talk a lot about elemental sulfur. But just the nature of our discussion, this conversation that we just had, should help you realize, because we contrasted elemental sulfur with other sulfur sources, that elemental sulfur is not the only kid on the block. There are other sources of sulfur as well that we can access. AMS, for instance, is one commonly used product that has sulfur within it. You can see the percentage of it there by weight. Gypsum is another one, another fairly common and often talked about source of sulfur, and it's about 17% of that product by weight. You can see some other sources of sulfur mentioned there as well. That wraps up session 3B. We're going to move on to session 4 here next time, and during that portion we're going to talk about some of the minor sources of sulfur in the soil. We've talked about the major sources now: fertilizer, atmospheric deposition, and the big player, organic sources of sulfur. Now we're going to move on to these more minor secondary sources of sulfur in the soil profile that the plant can access. Thanks for watching, and we'll talk to you later. We look forward to visiting with you soon on Burris Agronomy U.